All right, welcome to another deep dive. You know how it is you want to really get something, understand it inside and out, but without drowning in a sea of details. We get that.
Exactly. We all want those key insights, those aha moments where complex topics become clear.
That's what we're going for today. And the topic we're diving into, it's a cornerstone of electrical engineering, simplifying circuits, specifically circuits built with resistors.
Yeah, resistors are everywhere in electronics. They're like fundamental building blocks. But when you see a circuit diagram with a whole mess of resistors, it can be intimidating.
Absolutely. Yeah. And what we want to show you today is how, no matter how tangled that resistor network seems, you can break it down, simplify it, make it understandable.
And what's cool is that this isn't just some theoretical exercise. Understanding how to simplify these resistor circuits gives you a real grasp on how circuits actually work. It pops up in places you might not expect.
Like in everyday tech. Think about touchscreens.
Yeah.
You know, the ones that respond to pressure.
Yeah. Resistive touch screens. The principles we're talking about today are at the heart of how those screens figure out where you're touching.
Right. So for this deep dive, we're going to walk through four main areas. First, we'll tackle resistors in series, and in parallel, those are like the basic arrangements.
Then we'll move on to voltage dividers and current dividers. Those are clever circuits that let you get specific voltages or currents from your source.
After that, we'll unravel the workings of the Wheatstone bridge, a circuit used for super precise resistance measurements.
And finally, we'll tackle Delta-to-wye transformations, a technique that's like a secret weapon for simplifying really tough resistor networks.
All right, so let's kick things off with the fundamentals.
Hmm.
Resistors in series and in parallel. You see components connected in series. Think of them like links in a chain end to end, only one path for the electricity to follow.
Right, and what that means for the current is that it has to be the same through each component. There's just nowhere else for it to go. Imagine water flowing through a pipe. Same amount has to flow through every section.
Makes sense. And if we think about Kirchhoff's current law, you know, that rule that says the total current entering a point has to equal the total current leaving that point. Well, in a series circuit, there's no branching, no alternative paths, so the current has to be identical through all those resistors.
Precisely. Now, when we think about voltage, that's where Kirchhoff's voltage law comes in. That law says that the sum of all the voltage drops around any loop in a circuit has to equal the total voltage applied.
So in our series circuit, the voltage from the source gets split up across each resistor.
Exactly. Each resistor is kind of like an obstacle for the current, so it causes a voltage drop. You add up all those individual drops, you get back to the total voltage.
Got it. So each resistor gets a piece of the voltage pie.
Yeah.
Okay, so one key concept here is this idea of equivalent resistance. If you've got, say, a bunch of resistors in series, can you replace them all with a single resistor that has the same overall effect on the circuit?
You absolutely can. And for resistors in series, the equivalent resistance, that single resistor that could stand in for all of them, it's just the sum of their individual resistances. You add them up.
So if I had, let's say, a 1 ohm resistor, a 4 ohm resistor, and a 2 ohm resistor all in series, it would be like having one big 7 ohm resistor.
Exactly. The circuit wouldn't be able to tell the difference. And one important thing to remember is that this equivalent resistance, it's always going to be bigger than the biggest individual resistance in that series string. Makes sense if you think about it.
Yeah, it's like you're adding more obstacles in the way of the current, right?
Yep.
So the total resistance has to go up. I like the analogy they use in the book, the black box idea.
Oh, yeah, that's a good one.
Imagine you have a sealed box, can't see inside, but you can measure the resistance between the two terminals sticking out. If that box has a bunch of series resistors inside, you can swap them out for a single resistor with that equivalent resistance we calculated, and from the outside, you'd never know the difference.
Exactly. It's a really neat way to visualize it. All right, now let's switch gears and talk about parallel connections. How does that differ from series in terms of how things are hooked up?
Well, in a parallel connection, instead of being end-to-end, the components are connected across the same 2 points in the circuit, meaning they all share the same voltage difference across them. Think about it like a bunch of lights connected to the same battery. Each light gets the full voltage of the battery.
Perfect analogy. It's like multiple lanes on a highway, all starting at the same point and ending at the same point. So what happens to the current in a parallel circuit?
Right, so with our crusty Kirchhoff's current law, we know that the total current flowing into the junction where those parallel branches split, it has to divide up and flow through each of the resistors. The amount going through each branch depends on its resistance. Lower resistance, easier path, more current will flow that way.
Exactly. Now, just like with series resistors, we can find an equivalent resistance for parallel combinations. But the way we calculate it is a little trickier. Instead of adding directly, we add their reciprocals and then take the reciprocal of that sum. It's like 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, and so on.
Ah, okay, so a bit more involved than just straight addition. So what's the defining characteristic of this equivalent resistance in a parallel circuit?
Interestingly, the equivalent resistance in a parallel combination is always smaller than the smallest individual resistance in the group.
Huh. So the opposite of series. Why is that?
Because by giving the current multiple paths to flow, you're essentially making it easier for the current to get through. It's like adding more lanes to that highway, traffic flows smoother, there's less overall resistance. And speaking of making things easier, the book mentions this idea of conductance, which is basically the opposite of resistance. It's a measure of how easily current flows through something. And for parallel circuits, conductance just adds up directly.
Oh, so that's simpler. No reciprocals needed.
Yep. You can think of it this way. You're providing more paths for the current, so the overall ease with which current flows, or the conductance, just increases. And by the way, for the special case where you've got just two resistors in parallel, there's a handy formula. The equivalent resistance is the product of the two resistances divided by their sum.
Oh, that's a good one to remember.
Yeah.
Makes the math a bit easier. Okay, so let's bring this back to our real-world example, the resistive touchscreen. The source mentioned they can be modeled as grids of resistors. How do these series and parallel ideas come into play there?
Well, picture the touchscreen as having these layers of resistive material. When you press down on the screen, you're creating a connection between those layers.
Right, like closing a circuit at that point.
Exactly. And by doing that, you're changing the effective paths for the current to flow. It's like you're dynamically altering the series and parallel combinations of those resistors within the grid. And that changes the voltage distribution across the screen.
So by measuring those voltage changes, the device can figure out where you touched.
Precisely. It's a really clever application of these basic circuit principles. And, the source material even walks through an example problem where you use this series parallel reduction technique to figure out the currents flowing in a more complex circuit. Really shows how crucial these simplification methods are.
Okay, so we've laid a solid foundation with series and parallel resistors. Let's shift gears now and move on to part 2, voltage dividers and current dividers.
These are essential circuits for, well, dividing voltage and current, tailoring those levels to specific values you need in a circuit.
Sound pretty handy. So a voltage divider, I think I've seen those before. It's just two resistors in series, right? And you take the output voltage from between them. How does that actually divide the voltage?
It all comes down to Ohm's law and that series connection we just talked about. Remember, the same current flows through both resistors in a series circuit. And because of Ohm's law, the voltage drop across each resistor is directly proportional to its resistance. Bigger resistance, bigger voltage drop.
Okay, so the bigger resistor eats up more of the voltage.
Exactly. And that means the voltage at the point between the two resistors, that's going to be a fraction of the total source voltage. That fraction depends on the ratio of the individual resistances to the total resistance.
So if you have two resistors, let's call them R1 and R2, connected in series with a voltage source V's, the voltage across R2 would be, let me think, V's times R2 divided by the sum of R1 and R2.
You got it. That's the voltage divider formula. And just to confirm, the voltage across R1 would be V's times R1 divided by the same sum. It's a simple but powerful relationship.
Makes sense. So the output voltage you get from a voltage divider is always going to be less than the input voltage.
Always. It's a way of stepping down the voltage, getting a lower voltage from a higher voltage source, and it's used all over the place in electronics.
Now, the source mentions this idea of loading a voltage divider. It's when you connect another resistor, a load resistor, in parallel with one of the divider resistors. What happens when you do that?
Well, loading can change things up a bit. When you add that load resistor, you're essentially changing the equivalent resistance of that part of the circuit, right?
Right, because now you've got that parallel connection going on.
Exactly. And if that load resistance isn't much bigger than the resistances in the voltage divider itself, it'll start drawing a decent amount of current. And that can mess with your carefully calculated voltage division.
So your output voltage might not be what you expected.
Right. It'll usually drop a bit. That's why when you're designing a voltage divider, you got to keep in mind what you're going to connect to it, the load. You want the resistors in the divider to have much smaller values than the load resistance, so that load has minimal impact.
Makes sense. But the book also mentions that real-world resistors, they're not perfect, right? They have tolerances.
Oh yeah, tolerances are a real thing. Real resistors, they're not going to be exactly the value they say they are. They might be a little bit higher, a little bit lower within a certain percentage range. And that can introduce some error in your voltage divider output. Engineers always have to keep those tolerances in mind, especially when precise voltages are critical.
Right. It's never quite as ideal as on paper. Okay, we've got voltage dividers down. Now, how about current dividers? How do those work?
So a current divider, you use that when you've got a current source and you want to split that current up, send it through multiple paths. Typically, you would have two or more resistors in parallel.
So like creating branches for the current to flow through.
Exactly. And the way the current splits up, it's based on the resistances of those branches. It's inversely proportional, meaning the path with the lower resistance will carry more of the current.
The path of least resistance. Makes sense. So if we have, say, a total current, let's call it is, flowing into two parallel resistors, R1 and R2, how would we calculate how much current goes through each?
So the current flowing through R1 would be is times R2 divided by the sum of R1 and R2. Notice it's the other resistor's value that's in the numerator.
That's different from the voltage divider formula. It's the opposite resistor's value.
You got it. The current divider formula, it flips things around. The lower resistance gets the bigger share of the current. And just to confirm, the current through R2 would be is times R1 divided by the same sum.
Okay, that inverse relationship makes sense.
Yeah.
The source also provides formulas for when you have more than two resistors, like a whole bunch of them in series or parallel.
Right, they're generalized formulas. For n resistors in series, the voltage across any one of them is its resistance divided by the total equivalent resistance of all of them, multiplied by the total voltage. And for n resistors in parallel, the current through any one is the equivalent resistance of the whole parallel bunch divided by that particular resistor's resistance, multiplied by the total current.
And it's almost like the voltage and current divider formulas are flipped, like mirror images of each other.
That's a good way to put it. Voltage division, it's proportional to the individual resistance compared to the total. Current division, it's the inverse, proportional to the total compared to the individual.
Interesting how that works. The source even has an example where you combine both voltage and current division to solve for different values in a more complex circuit.
Yeah, it shows how these tools can be used in practice to analyze circuits step by step. Mastering these divider concepts is honestly key to understanding how so many electronic circuits work. They're everywhere.
All right, so we've tackled series and parallel resistors, voltage and current dividers. We're making good progress. Let's move on to part 3, the Wheatstone bridge. What's special about this circuit?
Well, the Wheatstone bridge, it's a very clever circuit configuration specifically for accurately measuring resistance values. Think of it like a super precise ohmmeter.
So if I need to measure the resistance of something very accurately, this is the tool to use.
It's a classic method still widely used today. What's unique about the Wheatstone bridge is its design. It's all about achieving balance.
Balance, how does that work?
So picture this. You have 4 resistors arranged in a diamond shape. We call it a bridge circuit. Across 2 opposite corners of this diamond, you connect a DC voltage source. And across the other 2 corners, you connect a sensitive current meter, usually called a galvanometer. Now, one of those resistors is adjustable. You can change its value. Another one is the unknown resistor, the one you're trying to measure. The other 2 resistors are fixed known values.
Okay, I can visualize that. So what's this balance thing?
You adjust that variable resistor until the galvanometer reads 0 current. Absolutely no current flowing through it. That's the balanced state.
Huh. So when that happens, what does it tell us about the unknown resistor?
Well, when the bridge is balanced, it means the voltages at those 2 points where the galvanometer is connected, they're exactly the same. No voltage difference, no current flow. And by applying Kirchhoff's laws to this balanced bridge, we find a very neat relationship. The unknown resistance is simply the ratio of those 2 fixed resistors, multiplied by the value of the variable resistor at balance.
So if I know the values of those fixed resistors, and I carefully adjust the variable resistor until I get 0 current, I can calculate the unknown resistance directly.
Exactly. It's a null measurement method.
Yeah.
You're looking for that point of 0 current. And that's what makes it so accurate. The precision depends on the accuracy of those known resistors and how sensitive your galvanometer is.
Makes sense. The book also mentions that you can vary the ratio of those fixed resistors. Why would you want to do that?
Changing that ratio lets you measure a wider range of unknown resistances accurately. If you're trying to measure a very small resistance, you'd use a smaller ratio to bring the required variable resistor value into a more manageable range. For a large resistance, you'd go for a larger ratio. It's about making sure your measurement stays within the most sensitive range of your instrument.
So it's a pretty versatile tool. But the source also talks about limitations, right? Like when dealing with extremely small or extremely large resistances.
Yeah, there are some challenges at the extremes. For very small resistances, even tiny voltages and currents can cause problems. You might get thermoelectric voltages at the connections, or the current itself might heat up the resistors and change their values. For very large resistances, leakage currents can mess things up. Those are tiny currents that can sneak through insulation.
So while it's super accurate within its range, you can't use it for everything. There's even an assessment problem in the source that involves a balanced Wheatstone bridge. Good way to test your understanding.
Absolutely. The Wheatstone bridge is a fantastic example of how clever circuit design and those fundamental electrical laws can be combined to create precise measurement techniques.
All right, so we've explored series and parallel resistors, voltage and current dividers, the Wheatstone bridge. We're on a roll. Let's move on to our final topic, Delta-to-wye equivalent circuits. This sounds like a technique for dealing with more complex resistor arrangements.
You got it. Delta and Y, these are two common configurations for connecting three resistors together. Delta, it forms a triangle, like the Greek letter delta, or sometimes it's called a pi network. Y, on the other hand, has three resistors connected to a central node, like the letter Y, or sometimes called a T network.
Okay, so why would you want to transform one into the other? What's the benefit?
Sometimes you come across these resistor networks that are just a pain to simplify, using only series and parallel combinations. The delta or Y arrangement might be in a way that makes it hard to break things down. But if you can transform that delta into an equivalent Y, or vice versa, the resulting circuit might suddenly become much easier to analyze.
So it's like a trick, a way to rearrange things so that you can then use your regular series and parallel tools.
Exactly. And the key is that these transformed circuits, they're electrically equivalent to the original at their terminals. Meaning if you had a black box with a delta network inside and another black box with the equivalent Y network, you wouldn't be able to tell them apart just by measuring the resistance between their terminals.
Oh, that's interesting. They behave the same way from the outside.
Exactly. And the Wheatstone bridge, it's a perfect example where this delta to Y transformation can be super useful, especially if you need to factor in the resistance of that galvanometer. You can often spot these delta or Y subnetworks within larger, more complex circuits.
Makes sense.
Yeah.
So how do you actually do this transformation? Are there specific formulas?
Oh, absolutely. There are sets of equations for going back and forth. For a delta network with resistors, let's call them raw, RB, and RC, connected in that triangle shape, you can calculate the equivalent Y network resistors. Let's call them R1, R2, and R3. And the formulas for those R1, R2, and R3, they involve combinations of those raw RB and RC values, like ratios of products to sums. And similarly, there are formulas to go back from Y to delta.
Looking at the source, it seems like for the Y network, each resistor is calculated as the product of the two delta resistors connected to the same node, divided by the sum of all three delta resistors. And for Y to delta, it looks a bit more involved, but still follows a pattern.
You've got the idea. The main point is that with these equations, you can swap one type of three-resistor network for another, and they'll behave the same way electrically. And that can often make a previously impossible-to-simplify circuit suddenly solvable.
The source even gives an example where you use a delta to Y transformation to simplify a circuit and find the current from a voltage source. It really highlights how powerful this technique can be.
Yeah, it's like adding a whole new dimension to your circuit analysis toolkit. It opens up a world of possibilities.
Now, let's go back to our resistive touchscreen example for a moment. We talked about how touching the screen creates a voltage division. Is there a direct connection between that and this delta to Y transformation idea?
Well, while the basic principle of a resistive touchscreen relies on that voltage division caused by the pressure of your touch, which changes the resistance, the underlying layers themselves, in more sophisticated designs, they might have patterns that could be analyzed using delta or Y concepts. But for the simplified model we discussed earlier, it's more about understanding how that touch creates a local voltage divider. The ability to analyze these complex resistive networks, whether through series parallel or delta to Y transformations, it gives you a broader foundation for understanding how current and voltage behave in any resistive system.
Right, so even if it's not a direct delta-wye transformation in the basic model, understanding these techniques is crucial for designing and analyzing those touchscreens.
Absolutely. It gives you the tools to understand the underlying mechanisms.
All right, so that brings us to the end of our deep dive into simplifying circuits using resistors. We've covered a lot of ground today, from series and parallel resistors to voltage and current dividers, the Wheatstone bridge, and delta-to-wye transformations.
We have. And these are really fundamental concepts. They're the building blocks for understanding more complex circuits and systems.
And it's been fascinating to see how these theoretical ideas connect to real-world technology, like those resistive touchscreens. They're all around us.
Hopefully, this deep dive has given you a solid understanding of these circuits, how to analyze them, and maybe even a new appreciation for the electronics that we use every day.
Absolutely. So next time you pick up your phone or use a touchscreen, maybe you'll think about those resistors and how they're working together. It's a whole new way to look at the world around us. Thank you for joining us for this deep dive into the world of resistors.
It's been a pleasure diving deep with you.
Until next time, keep exploring and keep learning.